So we're going to talk about electromechanical energy conversion. And what I'm going to show you is a general black box approach here, looking at a energy system. So that's what we've got right here. It's got electromagnetic components inside of it, and this system here, let me just probably put it, I'll just write system in the middle of this box right here. We have really two types of electromechanical energy conversion scenarios that we're interested in. We have actuators or motors. And the other one we have is generators, but we're going to talk about the actuator first. And graphically what this looks like is I have a system and I'm putting into that system a current and a flux. And what I'm getting out of that system is a force, and we call this, to match the textbook, force of the field. It's not a force field like Star Trek. It's the force of the field. And it produces motion, so position, movement in the x-axis. And so what I've just described here would be what's called a linear system. I could similarly have a rotational system, and I would put in a current and a flux, but I would get at a torque due to the field of the flux and a angular position theta. So we'll call this a rotational system. And what we're really doing is we're putting in energy. So there's energy input, or let me write it instead, electrical energy input. And we have an output of mechanical energy, and internal to this we have two things going on inside of this little box here. We've got a increase in energy or really a conversion of energy from the magnetic system. And I'll just call these, this is your magnetic system. Minus a losses or heat. So mathematically, in words, we've got energy input on one side of the equation, is equal to they say an increase, but it's really kind of a change. Let's see here. Well, I guess it is. It's an increase. It is an increase. An increase in energy because of the magnetic system minus losses. And then we could say, making this whole thing an equivalency. Let's see, I've got this written, it's not quite right. The energy output is equal to, I think a better way to write it, the energy output is equal to an energy input plus some increase in energy minus losses. And so this output is mechanical energy, and the input is electrical energy. And what that energy on the output is the force times the position. I'm just doing the linear system. The electrical energy input would be lambda times I, and then what we're going to get is okay, that was what was messing me up. I'm not reading my notes right. This should be minus an increase in energy, not a plus an increase in energy. And it's really kind of a mathematical thing here, that this is the energy from the magnetic system. We decided at the beginning to use this symbol W. So that's the energy from the, and whenever I put this subfield, that's due to magnetic, because there has to be some magnetic applied field to produce this. And then it would be minus the loss energy. So I'm going to take the derivative of both sides of this equation with respect to time. And what I'll end up getting is this. So we really don't get any energy output unless we have a movement in position, or either linear or angular position with time. And then on the other side of the equation, then you're going to get the derivative of the flux linkage times the current. Now we know that this is voltage. So it's voltage times current minus the derivative of the magnetic energy increase minus the losses. So we could just say that's I squared R losses. And now we're going to just ignore the losses for now, for the rest of the, just for the sake of trying to understand what we're working with here. So we have E times I minus this derivative of the magnetic energy with respect to time is equal to the force times the derivative of the position with respect to time. And that's what we have if we have an actuator. Any question about this from anybody? We haven't really hit any punchlines yet, but I'm just kind of putting this information out there. It looks like nothing I've said doesn't make sense. If there's something that doesn't seem right, let me know. But let's consider what we have if we have a generator. We could have a linear generator, in which case we would put into that generator a force, and there would be an associated movement, change in position. And then as a result, we would get a current out and a flux. Or if we have the more common rotational system, excuse me, we would put in a torque. There would be an angular movement, and we would get out a current. Let's see, what did I say? Yeah, we would get out current and flux as well. And then the equation that we would have in this case would be E times I for the linear system, which is where we're going to start. The input force times the derivative or change of position with time minus the, let's see, I think this is now going to be a positive. I need to double check to see if I wrote down the generator equation. Yeah. So now what we have is a positive change in energy. And minus the losses. And then we could just neglect this. And we get E times I and the only difference between these two equations is the sign here. Well, and the fact that we need to pay attention to what's on the left hand. Versus the left hand, we're getting a electrical. So this is an electrical output with the generator. And here we're getting a mechanical output with the motor. So next, what we want to do is we want to say let's take a look and consider the just consider the actuator for now. And we have this equation of force times a change in position with respect to time equal to the go back to this one here, the voltage in minus the energy. And I'm going to rearrange this equation and put the energy on the other side of the equation. Because if you haven't already guessed, what we're really trying to do is we're going to come up with an expression for this energy. And I'm going to rewrite it this way. Go back and write it in terms of flux. Now this is a little bit of a mathematical thing, but we're going to notice that we have these derivatives, but we can also say, well, I've got the derivative with respect to time on both sides of this equation, so we're just going to divide out the dt. And now what we have is a change in energy is equal to a change in flux times current minus a change in position times force. And what we have is now a differential equation from which we could derive an expression for the energy. So this is the magnetic energy. We talked a little bit about magnetic energy when we were talking about the core loss and the hysteresis loss. So what we need to do now is, if we want to find what this really is this is a differential equation for energy, magnetic energy. So if you wanted to solve for the energy, what would you do? Anybody want to just say something and also check to make sure everybody's hearing me? How would you solve for the energy?
Could you do separation of variables?
Well, that's kind of
We just integrate.
Yeah, you would just integrate. It'd be simpler than that. You're just going to integrate both sides of this equation. So essentially what we're saying is that the energy would be the integral of this. And now what you have is, this is maybe new to some people, but if you, I don't know how many of you have had controls classes or differential classes in differential equations, but when you're solving an integral that's involving more than one thing, it's helpful to identify what I would call a state variable. So a state variable is identifiable by finding whatever the D term is. Because as you solve for this integral, what you're going to end up coming up with is a graphically, you're trying to find a energy point here that exists at a given x value, I'll say that x naught, and a given lambda naught value. So you really have these two state variable axes, x and lambda. And you could, in order to come up with a completely general expression, you can take any path with respect to lambda and x, with respect to this at lambda and x, to integrate that path and come up with the energy. So I'm just kind of show you a random. There's like a random line that you could integrate over, and you could come up with a value at that point. So since it's random, we could pick a line that we really want to follow and make our life easier so we can actually come up with a solvable solution. And so we can pick two paths to get there. We could pick a path along the x-axis, and we just could pick a path along the y-axis right there. So if we do that, then we can write our differential equation like this. We're trying to find the energy at point x naught lambda naught at that point by an integration. So we would do that by integrating this first path, I could say the path 1, and then path 2. So integrating path 1, we would have an integral from 0 to this point x naught of FLD dx. And then we would take a second integral from 0 to lambda naught of I d lambda. And now what we would get from that is, first of all, along this first path line, if we have no flux, then we're not going to have any force. There's not going to be anything happening. So along the first line, then this would have to be 0. And then all we would end up with is this, a very simple expression here. The integral and so and I'm also going to write this a little bit more specifically, and we're going to say that the I is the current that is occurring at the position x0, but it could be varying with lambda. And now we also know that to recall that what is a lambda? Lambda is equal to the inductance times the current, right? And we're going to assume now that we might be able to have at a position x0, I'm rewriting this, I therefore is equal to lambda over L. So at a position of x0, we can get a current I x0 lambda divided by L at x0. And now we're going to plug this into this equation here. And now we have something that we can integrate and get something meaningful out of it. Lambda over L x0 d lambda. And the integral of this is lambda squared over 2 Lx0 evaluated at 0 and lambda 0. So the final expression is lambda 0 squared over 2L x0. So what we've done is we've found this point right here by doing a pretty general integration and come up with a pretty meaningful expression, which we can then generalize to the energy. Magnetic energy is a function of x, and lambda is equal to lambda squared over 2L as a function which is varying with x. So this is actually one of these very important equations that we're going to use. So I'm going to emphasize that for you. One of those ones that would go on your 8.5 by 11 piece of paper. And you'll say, okay, what's the use of this? So let's give an example to start with to try to understand things. So this is actually very similar to a homework problem that you were given, the plunger example problem. Before I give it, is there any question on this right now so far? No question. Okay. So let's consider a plunger which we had this structure like this. It was a magnetic structure, core material, but then we had this gap that we cut out of this material here. And that gap can move in an X direction. So we wound up with we ended up with if you recall that homework problem, we ended up with an equation for the inductance that was equal to mu naught. Oh, I didn't add in the turns. So let's do that. Here's our copper wire. And we're going to apply a current to this system, and it has N turns. And we're also going to assume that the mu relative in this is approaching infinite. If we don't do that, since we're doing this, we're actually going to end up with a pretty linear problem, and it's going to make we're going to be able to simplify our results as well to something that you've probably seen before. So the expression for this inductance is N squared. We have now a variable gap area with X. There are two gaps, right? There's a gap here, and there's a gap here. We're using G to represent that gap distance. So this would be over 2 times G, where the area of the gap, and in this case we're going to neglect fringing. It's the length of the stack times the width of the dimension D, which we're going to say is this dimension right here. We're going to say this is the length here, L times D, 1 minus X over D. So when this, that would tell us that if X equals 0, which means you're in the 0 position right here, the area of the gap is equal area of the gap at 0 is L times D. And if X is equal to any X, I'll just call it X naught, any X position, AG of X is equal to 1 minus X position over D times L times D. If X equals D, AG of X is equal to 1 minus D over D, L times D, so it's equal to 0. So the gap's varying between this position here or this value here and 0. Any question about that, or have I got everybody cleared everybody so far? So I'm going to take my energy expression and say that the energy is equal, we know is equal to the lambda x squared over 2 Lx. Now what I can do at this point is I can say, okay, well, I don't know what this is, so what am I going to do here? Well, let's go back to what we knew before. And because we have a linear system, and I want to make one thing clear when I say linear. I said there's linear that we refer to, which is movement in one direction. That's not the kind of linear we're talking about. We can also say linear as a linear system really is kind of a y equals mx plus b type of relationship between variables. There aren't any cosines or sines or logarithms or e to the x's or anything like that. Essentially, what is a linear system? A linear system looks like a straight line. So if I were going to say this is lambda and that's x, then I'm saying that at any x, I have a linear relationship between lambda and x. Okay, so I'm saying that you got two things. You got this, because that's what we're looking at, but we also have this. And that is what we're assuming right here. That's what we've got. So because of that, we can say that lambda x equals L of x times I of x. And now we can plug in F into this force expression. We can actually make it a function. I'm going to leave it on this left-hand side as lambda. But on the right-hand side of the expression, I've got now on the top L sub x Ix squared over 2 times Lx. And now if I simplify that, I get 1/2 Lx Ix squared. Anybody ever seen this expression before? 1/2 Li squared?
Yes.
Yeah, should look familiar to some of you. And so this is true for the linear system. Okay, so we have what we have been able to do so far with this plunger example is we've been able to find an energy. Now, one thing that made this linear system was what made this linear so we can ask that question. Number one, the current that we put into this, I'm going to say is equal to some constant current, I naught. So the corollary to this was if I is a function of x, and it's changing with x, then the system is not linear. For example, what if I of x, so we were saying up here, I'm going to make it really clear, I of x is equal to the same value everywhere. But if we said I of x is equal to some, and let me put this as a capital value here too. If we said it's inversely proportional to x, it's no longer linear. And we can't use this. And there's a very complicated example that the text goes through to show that. We're not going to take the time to do it in class if you're interested. But once we do the rest of the problem, we find the force. And you can go through this thing and prove that you cannot use this expression. You would have to go back and use this expression. So this is the general expression. And if we have time, we can give you an example of this. So this is for all cases, linear and nonlinear. And I'm going to give you a little bit of a hint. Here's linear. Here's a nonlinear system. Okay. So there's your nonlinear system. That's just an example. Another one is 2. If L, which is, you already know this, we've been through this with our chapter 2, L sub x, you have L, let me put it this way, L also changes with I. So if your L changes with I, an example of that would be saturation, right? Or a saturated core. In which case, remember you have your B and you've got your H with a core. Let's do our BH curve. Here's the linear region. So everything we could use in this region, we could use 1/2 Li squared. But once we get into this region here, we would have to use the general expression to find our energy. And if you remember that this B, as we went through Faraday's law, is proportional to lambda. And H is proportional to a current. So we could rewrite, and we're going to start thinking about these BH curves like this, a lambda I curve. So I could write the same thing here like this. So the lambda I curve. And we're going to come back to this in a moment and introduce a very important principle. But really going to be thinking about magnetic systems in terms of lambda I for a while, not BH. Any questions about that? Okay, so what about force? Because that's what we're really after. We're actually trying to talk about motors in this class. So if we had a linear motor, and this is a mechanically linear motor, or actuator as they're typically called, produces a force in one direction with power input. That's what this plunger thing is here. Can anybody think of a very common linear actuator that you've encountered? That you see all the time? Anybody know of one? No? You sure? No takers? Well, okay, so I'm a power electronics person, okay? So I'm going to say, I like power electronics because it's cool, and it involves a lot of different things, it involves digital controls, signal processing. If you want to find an area that has everything that's cool in electrical engineering, it would be power electronics, electromagnetics, and transistors. So it really has everything except for the really hard stuff. That's, in my mind, to understand, which was what you learned in EE 362, right? But it actually involves those things as well, especially with the new transistors that are coming out that have such fast edge rates. It starts to look like an electromagnetic system. But we used to call everything else, us power electronics people. This is when I used to work at Eaton, clunkatronics. Okay. So anything that goes clunk is clunkatronics. So that's basically what? Switches, right? Mechanical. So that's Now I think this stuff is pretty cool too. But I don't mean to be completely derogatory, but I call this as a clunkatronic type of a problem, Anything that goes clunk when you energize it, that's a linear switch, a clunkatronic. So what? That's a solenoid. You've got a lot of those in your car. You've got them fancy switches. You'd use solenoids. You've also got mechanical relays, circuit breakers. They use a lot of other physics too here, but the electromagnetic part of these things is linear. There's thermal involved in this guy, for example. He has a thermal that makes it quite nonlinear. But okay, so that's what we're talking about. So if we wanted to find the force, let's examine the energy, the derivative of the energy. And let's do this. I think someone said before you'd solve this problem by, was it separation of variables or something like that? This is where that part comes in. So we're going to take a derivative now, and we're going to say the derivative of energy is equal to the partial derivative of the energy. There's really two things that make my energy change. Partial derivative of the energy with respect to position evaluated at a specific value of flux linkage, times the dx, plus the partial derivative of the energy with respect to lambda evaluated at a specific position x naught times, I think I have to put a squiggly here, okay, so there we have it. Now we can compare this expression to our other differential equation that we showed you, that we solved by integral. And it looks like this. Okay, so what we can do from this is we can say, well, we're really trying to find force, and this expression here, right here, this expression looks like this. I mean, on the left-hand side and the right-hand, it's the same, but the right-hand sides are different, so there must be a correlation. So we have a d lambda here, and we have a d lambda here, and we have a dx here, and we have a dx here. So really what we're after is we're after the force. So we're going to find the thing that correlates to this coefficient. So this is a coefficient right here. And that would be equal to negative f sub FLD. So the general expression for force is F due to the field equal to the negative partial derivative of the energy with respect to x evaluated at a constant or a specific point of flux. This is your general expression right here, which I'm going to emphasize. So if someone was to give you an expression for the force as a function of x, if you take the derivative of that, you would evaluate it at a specific flux. You would get the force. We also know that we found an expression, a general expression for energy which was equal to this. So we could also plug this expression into that. Now we have to, what we would do is we would basically, let me make it a little clearer. Let's plug the energy as a function of x at a specific lambda naught. So that's lambda naught squared over 2Lx. We're going to plug that into here and take the derivative. And so the force as a function of x ends up being equal to this, negative of the partial derivative with respect to x of lambda naught squared over 2 times Lx. That's the same as saying take the derivative of lambda naught squared over 2 times L of x to the negative 1 power. Just to kind of spell this all out, right? So the basic derivative ends up being this. This lambda naught squared over 2 comes out, and you end up with the derivative. This is a general expression of the inductance with respect to x. So there's your second general expression that you can use. You can use
Quick question.
this or the other. Yeah.
Why does the negative drop off?
Because of the doing the derivative, right?
Okay.
So you do the derivative, you're going to get negative
right.
1 times the derivative of Lx dx.
That's right. Thank you.
Yep. And it's a general expression, right? So if you if you have x, if you have L sub x, use this. If you have the energy, use this. So you could actually always come back to this one here, but then you would have to calculate the energy. If you already had Lx, you could save yourself a page of work. So if we go back to our plunger example, we have an L of x in that plunger example, right? If we go back up to that example, it was this expression right here. So let's just use that, take the derivative of that, and we can find the force. So there you go there. So the derivative of that x is equal to remember, mu naught n squared LD 1 minus x over d 2 times g. So this is all a constant right here. We'll just call this k. So we have, trying to take the derivative of this whole thing. And so that would be negative k over d. That would be the dl. That's the derivative right there. And then if we wanted to find the force, it would be the lambda evaluated at a specific position, because we'll have a different force at different positions of the plunger. The force will be varying. And so we would say that this is L, some position of x times the current that we had, divided by 2. So this would be the force at a specific x and a specific lambda. So all we would really need to do is plug in this function here that we had for L. So that would have been mu naught n squared LD 1 minus x over d, but we're at some position, over 2g times negative k over d. So there's our force. Again, the thing what you're doing is you're evaluating the force at specific, these are specific points. Trying to really emphasize this, because if you don't do that, you end up with some horrific expression that's going to give you the wrong answer. Now you guys will have a few problems on the next homework after. So here's an example right here that I can show you. This is the plunger example numerically worked out in your note, in your handout that I gave you. You've got plugging in all the values that were given. And this problem comes from the textbook. So this is a 6th edition.
If you don't mind, where we can find this handout and what module?
I put the handout. It is module 4. At the beginning of class, I said it's module 4, which is up on Canvas already. And what this problem eventually gives you are different inductances at different position values. and it gives you, so here's your inductance plot with position, and you can find a force. And as the position moves out towards the position of D, x equal D, you approach zero force. So you've got maximum force when the plunger is lined up at the x equals 0 point, negative 0.07 newtons. And then it keeps going down. And then I've got that in these notes right here, working that out for you. Okay, so I think we're at a pretty good position. Next time I'm going to talk to you about co-energy, and I think actually I made up some time, which this is actually good for you guys. And then we can go into multi-winding systems, or we might show some more complicated examples. Once we get to multi-winding, we can wrap up chapter 3 and move on to the really interesting stuff of the class, which is the motors and the generators.